at the Institute of Construction and Infrastructure Management at ETH Zurich. And this research was conducted in collaboration with the University of Waterloo as well. So I'll first introduce the research methodology and the background information of the nuclear project chosen for the empirical analysis. And then the subsequent analyses, including the defect root cause analysis and the geometric defect impact analysis, will be discussed as well. And lastly, I will summarize the conclusions in the future work. So project physical complexity in prefabrication may be affected by the component and module size dimensions, along with geometry of the overall module. Quality checks in the current modular fabrication sector may occur in the form of documented quality control by qualified staff or undocumented self-checks by the craft workers themselves. Now, to rework items that fail quality checks, the process includes taking the modules apart, reunderstanding the individual components again, attaching the pieces together, and then conducting another quality check. Now, as you can imagine, this is a significant waste of resources, resulting in reduced overall productivity, represented by additional time and manpower spent on correcting the errors. To improve the productivity and continuous flow of prefabrication and construction, it is necessary to identify and better understand non-conformances along the project processes that would cause reworking. A number of studies have focused on developing real-time monitoring technologies and software to detect defects of construction components. However, less attention is received to examine the frequency of defects and non-conformances, as well as their impact on project performance, such as cost and time. It is partly due to the lack of empirical project information available for analyzing the non-conformance issues and their impact. A prefabrication and offset fabrication research have been reaping growing interest over the years, as well as in practice. Its potential for increased project performance offers improvement in construction quality, productivity, cost, and schedule. It is becoming an appealing and effective alternative to traditional stick-built construction. As a fundamentally distinct approach to construction, there are varying risks in prefabrication compared to a traditional stick-built method, increasing demands and complexity to aspects of project organization, engineering, procurement, planning, or transportation. Most studies in the literature emphasize the importance of quick identification of risks and potential quality problems, but the comprehensive understanding of non-conformance issues resulting from those risks have been missing from the current body of knowledge. Therefore, an empirical analysis regarding the non-conformance root cause and their impact on project time and schedule performance is required to fill the gap. To understand the types of non-conformances, their frequency of occurrence within the project, as well as their impact on the project cost and schedule, the team collaborated with a major fabricator in the construction industry, and the methodology as shown here is followed throughout the research. So first we identify the project, we collect the data, we process the data, we analyze the data, and then we draw conclusions from those analyses. The research team chose one of the industry partners' completed nuclear project, which has a comprehensive data log of non-conformance for this case study analysis. Now, due to the complex nature of this nuclear project, the information recorded were of higher granularity than other non-nuclear projects. The nuclear modules range in size from only 200 pounds to 102,000 pounds. The right side illustrates some of the 3D design of modules. Each module contains metal components to mechanical systems within the nuclear power plants, such as passive containment cooling, passive core cooling, or fire protection. Given the design complexity of each module and the need to adhere to nuclear operational and safety requirements, they also have several challenges throughout the project, including the management of the high number of system code changes, ensuring the quality requirements of each system are met, or modular frame construction with mega beam and non-standard truss geometries, assembly, welding, and inspections of frames, spools, and supports in a tight and complex geometry, or welding of high-strength steel requiring specialized weld procedures and regimented pre-heat and post-weld heating cycles. In accordance with the industry partner's internal quality control procedure, each non-conformance report is assigned a defect code to reflect the root cause of its non-conformance. These defect codes are categorized under 5 broad types, which are procurement issue, material issue from vendor, fabrication or construction issue, engineering or document control issue, or free issue material from customer. These 5 categories encompass almost all possible non-conformances a shop might experience. Material liabilities are differentiated between materials procured through vendors and those supplied by the owner. They are considered as external responsibilities through no fault of the fabrication shop. On the other hand, drafting errors and omissions, as well as fabrication miscues, are viewed as internal accountabilities, where craft workers, such as fitters and welders, are responsible for rectifying their identified non-conformance. Now, a total of 33 defect codes as identified in the procedure reflect the specific root cause of each non-conformance. All 1,179 non-conformance reports from the project were analyzed for a defect code, as well as the specific nuclear module affected. This table here summarizes the frequency of each defect code as documented in the data log. Now, for clarity, the defect codes related to geometric nonconformance are highlighted in gray here. This figure displays the module difference in geometric defect code proportion compared to the baseline average for the project. While it is not clear how module complexity will affect geometric nonconformance, it is evident from the figure that defect code 2.9, which represent a material dimensional issue, and defect code 3.3, which represent fabrication dimensional issue, are the 2 most frequently cited nonconformance. Although each NCR in the data log summarizes information such as the module affected, description of nonconformance, as well as the remedy proposal, it is almost impossible to cross-reference a project change order to a specific nonconformance root cause. Consequently, a preliminary estimate was carried out to assess the cost and time impact of correcting geometric-related issues. An interview was conducted with the fabrication manager who oversaw the entire nuclear project, having experience handling almost all the issues reported in the data log, including proposal defect remedies and overseeing their execution. Of the 693 geometric-related nonconformances, 84 were sampled, and this is based on having a confidence level of 95% that the real value will be within plus or minus 10%. During the interview with the manager, these sample NCR were reviewed individually for the nonconformance root cause and further assessed for the impact on a nuclear project. The table summarizes the number of samples from each defect code that constitute the estimate, as well as the statistics of estimated cost and time impact of the 84 sample geometric nonconformances. As shown in the table here, the average cost impact of sample geometric nonconformance is almost $1,000, and the time impact is approximately 14.5 man-hours. The results of the estimate are evaluated as well to characterize the sample data, which will allow curve fitting of probability distributions. The 2 top figures represent the cost and time impact histograms, and probability paper plotting is used to verify assumed probability distribution. 3 distributions were assessed, including normal, log normal, and Weibull distribution. Due to the linear relationship of the plot, the coefficient of determination can be used to measure how well a linear regression model fits the data set. Comparing the 3 distributions, it was found that log normal distribution had the strongest linear association, as it had the highest R-square value for both time and cost impact metrics, as shown in the bottom 2 figures here. In summary, there are some key findings from the non-conformance root cause analysis of the nuclear project case study. According to the partner's internal quality control procedure, 5 categories are used to distinguish general liabilities, can be internal or external, of non-conformance, as well as at which stage along the project the non-conformance occurred, which can be during material receipt or during fabrication. A total of 33 defect codes are classified under these 5 broad categories, specific to the type of non-conformance observed. Upon qualitative analysis of all documented NCRs, it was found that nearly 60% of all reported issues during the 3-year fabrication cycle were actually geometric in nature. Now, within this geometric NCR, over half of them are issues concerning dimension and tolerance for incoming materials and fabrication. And in the interest of understanding the impact of these issues on the project, Adey for NCR was sampled for evaluation. And based on the estimate, the average cost impact is almost $1,000, and the average time impact is 14.5 man hours. And they account for additional resources required to rework and to release the assembly. And the analysis confirms that both the impact metrics conform very closely to local distributions. It should be noted that this is the only data log available where the non-conformance are tracked and documented throughout the project's lifecycle within the fabrication shop. However, the methodology may be applied to other prefabrication projects in the industry, and specifically on the classification of defect codes, as well as the need to address geometric-related non-conformance during fabrication. Now, the data log doesn't include non-conformance reported at project site, meaning the impact does not account for fabrication errors that are overlooked before shipment, or any liability dispute between the fabricator and the site installation team. Additional costs may also be considered to rework any errors, which include crew traveling, lodging, schedule change, and modules transport. These expenses can amount to hundreds of thousands of dollars, depending on the project. And this necessitates accurate and precise documentation of the final assembly before release the fabrication shop to project site. Now, with 3D scanning becoming increasingly affordable and accurate for industrial use, it could function as a tool for geometric quality control during material receipt and fabrication in process check. And this is my presentation, and I look forward to any questions you may have. Thank you.
All right. Thank you. Thank you, Steven. No questions there, but I have one. Yeah. I read in your paper that you mentioned actually in the conclusion